I'm happy to introduce our speaker of the session, Dr. Ashiq Ahamed. Dr. Ashiq is currently the sustainability lead at the Pragmatic Semiconductor Limited, the United Kingdom, and he has expertise in the area of environmental sustainability assessments for semiconductor manufacturing. So he has worked with industry and university partners on a diverse array of life cycle analysis involving systems with significant complexities and challenges, including high-tech niche areas. His research works published in this domain are widely cited as well. So his expertise involving assessment of variety of technological areas in key differentiator in this field. Dr. Ashiq earned his PhD from Abu Academic University, Finland, and has a master's degree from Nanyang Technological University, Singapore. With that, I would like to invite Dr. Ashiq Ahamed to the stage to deliver his presentation. Ashiq?
Thank you, Dayan. Hello, everyone. I'm Ashiq, the sustainability lead at Pragmatic, and I'm here to share about our technology, FlexICs, a low-carbon tech enabling a low-carbon economy. Let's get into the presentation. So, modern electronics possess a remarkable capacity to advance human society. For semiconductors, there is a tremendous market opportunity across every single industry and sector. The digital transformation is impacting every facet of business and our everyday lives. Recently, a McKinsey report estimates that the global value of IoT alone to be up to about 12.5 trillion by 2030, and amplifying the level of connectivity to encompass billions of smart items and Internet of Everything could see that figure soar further. It supports a massive chip demand to service the Internet of Everything application. So, however, expanding the legacy chip production isn't easy. Uses older 200mm equipment and less readily available. And building new fab is costly and time consuming. And the profit margins aren't easier to achieve, and the equipment depreciates over time. But this equipment, unlike cutting edge production methods, isn't very sustainable as well. So a new paradigm is needed to unleash the potential of Internet of Everything. On the other hand, sustainability has become a global challenge. But then the opportunity is as much an environmental one as an economic one. So perhaps even more so as highlighted earlier than the one highlighted earlier. So the impact of climate change are growing more pressing by the day. A 55% reduction by 2030 would be needed to keep the goals of the Paris Agreement on track. But commitments for 2030 are projected to reduce emissions by only 7.5%. So to achieve the net zero by 2050, digital technologies will play a major role. Research conducted with Accenture in conjunction with the World Economic Forum has found that deploying digital technologies could reduce emissions by as much as 20% by 2050. So digital technologies are a key factor to enable the sustainable development. And there is no digital technology transformation without semiconductors. So, but we need to be mindful of the carbon impact of adding intelligence everywhere. So, however, electronics manufacturing has poor environmental record as they are typically resource and energy intensive, and often they are over-engineered. As the data gathering devices become more ubiquitous, we need new technologies to deliver more sustainable intelligence on agile, scalable, and localizable sources of supply across the spectrum of compute demands from cloud to edge and right down to device and item level. At Pragmatic, we have got a unique proposition. So FlexICs, flexible ultra-thin alternative to silicon semiconductors. We are using standard semiconductor 300mm tooling to produce our 300mm wafer, but we are innovating at a material and process level to deliver semiconductors with a significantly lower carbon footprint. So we predominantly use less energy due to the lower temperatures that we have and less intensive processing steps. Less water as well, and we avoid the PFCs and other high global warming potential gases and chemicals. So the result is our chips have a carbon footprint that's orders of magnitude less than an equivalent silicon implementation. Pragmatic, we are a world leader in ultra-low cost flexible chips. We are headquartered in Cambridge with about 330 plus employees, and recently we have closed. To date, we have been funded up to 300 million pounds, and we have a manufacturing facility based in Durham, which is a pragmatic park, a 60,000 square meter production site, which can accommodate about 9 300 FlexIC foundry lines. Pragmatic is basically revolutionizing the semiconductor manufacturing. So we have a breakthrough 300 wafer fabrication, which is entering volume production. So each production line is capable of producing billions of FlexICs per year. We deliver radical reductions in production cycle times, thinking of days versus months in a typical silicon foundry, and very low chip development and production cost. So essentially, we have a very high volume capacity and fast production with low cost and with a compact footprint to enable the semiconductor production. So this is a short video about our facility based in Durham. So currently we have the first line of foundry FlexIC ongoing, and which further has a capacity to expand it to 8 more lines within the same complex. So each of which would have a capacity of over billions of ICs per year. So the per FlexIC line, the area that would be required would be less than 600 square meters, and then within this space we would be able to locate 9 FlexIC lines. What are FlexICs? So FlexICs are optimized exactly for purpose, constructed constructed with alternative materials, removing energy-intensive steps from typical processes, and reduced water consumption and greenhouse gas emission and VOC reduction. Inherently, we have a low environmental impact compared to typical silicon nodes, and the market opportunities enable us to replace silicon in low-end applications and enable new applications as well. Next, I would like to touch on life cycle analysis, which is called LCA in short, and it is basically a tool to evaluate the environmental impacts, and it adopts a systems approach to material and energy flows and provides a comprehensive insight into the environmental hotspots of the system, and then it offers a holistic perspective of the environmental impacts. So typically it is assessed from cradle to gate, which is from raw material extraction until the end of life, or grave, and cradle to gate, which is from the extraction to the product being produced. So it is kind of an essential thing to evaluate the environmental footprint, including the carbon footprint. So
in progress.
There are about 18 other impact indicators, but here we would concentrate on the carbon footprint. So we conducted a LCA for our FlexICs, so which evaluated right from the raw material extraction to the finished product, so including all the stages in the production and accounting for their footprints, which was a systems analysis. And we assessed what and how much is being used and consumed, and it helped us to map the entire material flows from extraction to disposal, accounting for the energy consumption and source of the energy. It also helps to trace the upstream and downstream transportation activities involved. Based on this, we derived the footprint of a typical FlexICs, which is less than about half a gram CO2 equivalent per FlexIC, and which is orders of magnitude lower than a comparable silicon node. We basically used ISO standards to conduct this LCA, and This gives us a very comprehensive insight into our overall process and allows us to evaluate it and identify the hotspots. However, I like to highlight that there were several challenges of conducting LCAs for such a complex system. So the first thing is the data. So not every required data were available, and the quantities weren't available ready. So we had to gather those data from our own fab lines, and there's no prior eye as well. So no previous examples or reports of how it is done, and the inherent complexity of the manufacturing process itself uh, like was challenging to conduct the LCA because it required multiple levels of LCAs within an LCA. So, and then non-availability of data sets. That's again, so for LCAs, we rely upon certain databases maintained by the international organization. So within those, we don't really have all the essential data sets that we require to conduct LCA. So to manage the gap, we had to come up with our own assessments and gather data additionally. So these were some of the challenges, and that is one of the reasons why we don't see many LCAs being conducted for high-end technologies, and also for other silicon nodes. We don't really see LCA results reported much. And however, LCAs are essential to understand our hotspots and enable informed decisions to minimize the. So with the help of LCAs, we were able to identify our carbon footprint, and also internally, we were able to achieve and make use of the assessment for our continual development plans for the future. So fortunately, we do have already have safer chemicals and gases that is being used in the system, and several advantages compared to the alternatives. But then we also were able to identify further actions that we could take upon and improve the footprint further going down the line. So these are some of the key areas that we are focusing on currently to further minimize the footprint from where we are currently. So one is improve the, have more safer chemicals and gases, and reduce the wastewater emissions. So we do plan to recover and reuse about 80% of our wastewater, and further optimize the process. So since we have our first line up and running currently, but we would be able to further optimize it going forward, and we will be able to identify avenues to improve further. And supplier buy-ins is essential, and it's one of the key areas that we think is needed for our technology, because even though we could optimize our own process as much as possible, we do have chemicals and materials that is being procured and used in the system. So we are engaging with our suppliers, and we are coming up with long-term plans to minimize their footprint, and eventually which would improve our footprint as well. And the other advantage with our technology is decentralized production. So once we are able to deploy our fabs to everywhere, and that would help us to avoid the transportation activities along with it. So these are the areas that we would be focusing on in the near future. So far, I explained about how FlexICs have a lower carbon footprint, and how it fares with its competitors. Now I'll go into show how it enables a low carbon economy with examples of certain use cases. So the possible applications of FlexICs. So we currently look into NFCs, RFIDs, and sensor display and compute. So basically, we categorize into 3 themes for our applications. One is connect, sense, and compute for the near future. So basically, every industry is looking towards new technologies to drive towards a greener future. So there are new use cases for us beyond silicon, thanks to the cost and form factor of our technology. And where the economics of silicon chips doesn't make sense, we can penetrate that application. And the additional advantage is that not only can the FlexICs provide the same functionality as silicon chip, but due to its design and form factor, it reduces the material needed in the RFID antenna. So it has a consequential effect that it lowers the amount of antenna material that is required essentially. The applications that are suitable for a low carbon economy. So one is enabling circular economy and enabling food waste reduction, smart travel, and optimized consumer goods value chain. So these are some of the key applications that could enable a low carbon economy. And of these, I'll highlight two specific examples and our experience with those. So for circular economy, it is essentially retaining, it means essentially retaining a resource or material for the longest possible period in a functioning state. So adopting circular packaging solutions enables a functioning circular economy. So within that offering, there comes the digital deposit return schemes, which is NFC-enabled smart return points. It involves consumer engagement and reusable packaging. And then the next would be packaging as a service. So when you have a circular economy, you could have a packaging as a service where the ownership of the packaging itself could be adopted by certain businesses, and providing reusable assets and asset tracking and reverse supply chain optimization. So this is other area that could be enabled with technology. And automated industrial sorting, which would be again a key thing for the circular economy, because when you want to reuse the packaging and products in a circular chain, then probably you should have the capacity to sort it accurately, and it requires a lot of data analytics and reporting. So particularly because the circular economy requires a higher return rate for reusable systems to sustain it. So at least about 95% return rate is advised. So that would be important for like enabling the circular economy and to sustain it. And then looking at consumer engagement, so there will be smart packaging and personalized content and brand loyalty that could be enabled with the technology for this application. And supply chain traceability. So traceability at scale is challenging. So with the technology, it could be streamlined. And digital product passports are another important area. Because of the numerous participants in the system, information on the materials and waste management routes would be essential, which could be offered by the digital product passports. And finally, food waste reduction. So we could deploy a technology that senses order and temperature, and it also offers a dynamic use by date. So these are some of the applications or the implementations that would be possible within the circular economy with our technology. And to transition from the linear to circular economy, these are the 9R frameworks. And so the typical framework of transitioning is from the bottom of the table, which is R9 to R0. So currently the majority is with recover and recycle, which is R9 and R8. So we do some of repurposing, remanufacturing, refurbishing, and repairing and reusing every here and there. But then we need to move higher up the ladder, and adopting the technology will enable this transition and enable us to reduce our waste and reuse our materials for the longest possible period within the circular chain. So to share with you, recently we were awarded a project with the Innovate UK to lead on the typical reuse system. So which was the project was called TRACE, and which stands for technology-enabled reusable assets for circular economy. So here we evaluated the application of NFCs in circular systems, and we evaluated the environmental impacts of the circular system, and then estimated the additional footprint of adding an NFC tag to the reuse system. So these were the key objectives of that project. So we conducted an LCA for this reuse system, and we evaluated the entire value chain, which involved from raw material extraction, manufacturing, going to a pack house, distribution center, store, retail, consumer, and back to the distribution center, and then an additional step of sorting and washing, which was enabled by the NFC as well. And then at the end of its life, it would be recycled or disposed. So we evaluated this entire value chain within the scope of this project, and the system boundary was very comprehensive, and the LCA included all the possible stages, and the assessment was conducted for about for deploying or for distributing half a kg of tomatoes in a PET packaging. So which was in the form of a tray or a punnet. So the results from this study was really helpful for us to understand the system further, and we assessed about 18 impact categories overall, and the most significant ones are global warming potential, terrestrial ecotoxicity potential, human toxicities, and fossil resource scarcity potential. So since there's a lot of land-based activities involved, sorry, the terrestrial ecotoxicity was significantly higher. And for this talk, I think it would be worth to focus on the global warming potential, which was assessed further deeper into this, assessed further deeper. And so we included all the stages, right from tray production, crate production, pallets, and all the transportation activities, sorting, washing, wastewater treatment, and end-of-life management. So essentially, the different transportations accounted for about 27% of the footprint. And then the sorting and washing stages contributed to about 12%. So these were two of the significant areas that needs improvement further down the line. And then the FlexICs, which the NFC tags that we used contributed less than 1% to the overall footprint, which was really insightful for us. And especially if it can improve the return rates of this overall system and enable tracing of the assets, then it is very much a value addition to the overall system, and it justifies the reason why such a system would benefit immensely from adding an NFC tag to it. And sorry, and the transportation activity, we have to be aware that like within the different transportations involved, we could only map what is possible in the current state. So as the circular economy gets implemented and matures, probably those activities would get further optimized, and then the footprint of those could be reduced from those optimizations and reduction of distances that needs to be traveled further down the line. So. And next example I would like to highlight is the food waste reduction potential. So basically about 30% of the food produced is lost or wasted, and 40% of it occurs at retailers and consumers. So NFC Sense from using FlexICs enables item level insights and provides product provenance and impact conditions. So we are able to incorporate sensing for temperature, moisture, and volatile gases within this, and then which would eventually enable item level traceability and allow us to price dynamically and add a dynamic use by dates to this packaging, and then eventually it would help us to reduce the waste. And overall, we aspire for a more intelligent and sustainable future. So for Pragmatic, these are the trajectory of capabilities with FlexICs, offering from right from anti-tamper and sensing solutions, which we are already working currently, to circular economy solutions in the upcoming years. So there are wide range of applications with specific use cases through the current and next generation products down the pipeline. So as to conclude, FlexICs typically have a lower footprint, so it is a go-to product for applications it can support. particularly when you compare to a typical silicon node. And however, it is important to assess and balance the technical capabilities with environmental implications to understand whether if it is a great value addition to the system that would be enabled. And also, it also helps to replace conventional electronics and create new market opportunities. So this is a key thing for us. And however, going forward, it is always best to assess the entire life cycle from cradle to grave of that system that we are going to implement the technology with, and uh, and make the decision whether if it is a value addition again. So I also think it is critical for a sustainable future. To conclude, like, our mission is to see our sustainable technology deployed in trillions of smart objects over the next decade. However, we would want to like progress with care and ensure that wherever we are entering, we are adding value to the system rather than otherwise. Thank you, and I'm open for any questions if there are any.
Okay, thank you, Ashiq, for the nice talk and perspective of semiconductor manufacturing with a low carbon footprint. So we are open to questions. So please enter questions into the chat box. I think we have one question from Charlie. So he's asking, what things can I do to support or participate in the circular economy?
That's a good question. Thank you, Charlie. To participate in the circular economy, you probably would have to adopt to a more like circular usage of the materials that you consume. For example, in the packaging system, there have been certain implementations here and there on trying out circular systems. For example, the University of Sheffield introduced reusable coffee cups and things like that. So for us to go forward with those kind of implementations, we need a higher usage rate. And unfortunately, in one of the projects that they had to call it back because of less usage rate. So we generally have to be more open to reusable assets and reusable materials within the circular system. So that's something that we could do, and probably try to recycle and return as much as possible, like in supermarkets and other areas where they retake those expired products and like reusable materials.
We should support more recyclable products in any of the consumer products which we're using. That's the best way to participate. That's your comment, right?
Yeah.
So the other question from Charlie is, what circular economy technologies have the biggest effect now or in the future?
I think the reusable assets is gaining attention, and there is a reverse logistics that is important to be to enable the circular economy. So those are the things that are coming in place, and we have to move from linear usage of materials to circular usage. So.
And he's asking, what's your favorite application of your Flex technologies? Which technology which you promote?
I should say NFCs because that's what we have tried few applications for that, and it has been really insightful for us. And also looking into our experience, like how it could add value to circular economy solutions. That is something that I like it, and I would recommend. So, I mean, there are QR codes which are in place already, but for the biggest challenge is in the sorting stage, where it requires a line of sight to be scanned and then sorted. So I mean, even within our projects, we tried that, and yeah, it was a key differentiator for our technology to enable that sorting, and at scale was really important. Yeah.
So I have a follow-up question following this Charlie's comment. So are your NFC tags are disposable or fully eco-friendly? or is it?
It is recyclable. So we have conducted a recyclability experiments in collaboration with the University of Manchester. So essentially, they are recyclable in the form that, I mean, it might not be possible for us to get it back into our electronics supply chain, but say, for example, if it is being applied to a plastic packaging, then probably it could be recycled along with it. In the case of mechanical recycling, there would be tiny bits of antenna material that would be left in the recycled plastics. So what happens is that it might not be possible for us to put it back into food contact applications, but other applications could very well continue as is. But apart from mechanical recycling, there is a possibility of chemical recycling, thermochemical recycling, or other forms of recycling that could potentially be deployed. And within those options, I think we don't see any challenges of recycling the packaging itself. The electronics or the chip itself would have to, like, if it is being detached from the packaging that it is being applied to, then probably it is best for it to go through electronic recycling processes where they use chemicals to extract the resources. But then otherwise, yeah, we don't see challenges in the recyclability of it.
Mm-hmm. Do you see a potential in coming, I mean, following up with your recyclability? Do you see a potential we can implement some strategies at the designing of IC stage itself, where we can design this IC so that after post service, you can disassemble component wise and make a similar component from the used system? So is it possible to?
That it is definitely possible. It's not that since we are able to assemble it, we should be able to disassemble it and reuse it. But then the challenge here is the recollection of the material, right? So once it enters the market and it gets deployed to several different packaging items, so collecting it back into one roof is much more challenging, and potentially you might have a more environmental implication doing the collection itself, right? So these chips are, or even the NFC level, these are of like few grams, and to collect a reasonable amount to recycle, you would need millions, if not billions, of chips and NFCs back into the system for you to make economical and environmental sense of recycling those. So that would be much later, I believe, because we are still trying to recycle plastics and reuse plastics and other bigger materials that we use in our day-to-day activities to make sense of those recycling and reuse systems. So once that is being fully established, and once we have our fully functional circular systems, and once we have optimized these major challenges that we currently have, then probably it would be worth for us to look into recycling these chip level components back into its specific applications. But currently it's much more expensive in the sense economically as well as environmentally to do it now. Yeah. So eventually in future we should be thinking about it, but not at the moment.
Looking at the economic point of view, so you think implementing these strategies would increase the cost of the chip, so that is a major barrier to implement a sustainable.
Not the production cost itself. I think that would be covered with the cost price of these chips being sold to its consumers. But the challenge is to recover them, and the cost involved in recovering and recycling them, and also like thinking about collecting back billions of or millions or billions of chips back into the system would require so much activity to enable that collection back. So the footprint of those activities might be significantly higher currently, since we already don't have a system to that we could rely upon. So that's the challenge. It's not about the production cost, but the end of life cost that we need to consider.
Okay, so we have another question from Mark Underwood, and he's asking, did you find that ISO 14040 and 44 were adequate, in your opinion, to assessing a relevant aspect of system life cycle?
Okay, that's a good question. So these are basically guidelines. So it is not significant enough for us to like, or I wouldn't say it is adequate. So these are just guidelines. So based on these guidelines, we tick certain boxes when we conduct assessments, but that is not all, and it doesn't really help a new person who's conducting an LCA to do such an elaborate activity of conducting a life cycle. So yeah, we generally try to stick to these guidelines, but definitely they are not adequate. Yeah.
Hmm. So looking at your numbers, you mentioned the water consumption recyclability. You mentioned 80% of water is recyclable after your FlexICs production. So where this number 80% stands in terms of the state of the art, say a global foundry or Intel foundry manufacturing a chip. So what is the percentage of water consumption currently they are recycling? Is it you
Okay.
made a significant
No,
improvement?
we don't recycle 80% yet. So we aspire to do that. So that I want to make clear of that. Typically, the silicon foundries, they use about 3,500 to 4,000 liters per wafer, whereas we use about 35 liters per wafer, which is 100 times lower.
Yeah.
So we already make a significant savings in that
Okay.
area. But then, like looking internally for our own aspirations, we still try to we still would like to recover and recycle up to 80% of the 35 liters we use per wafer. But then there are a few projects that are ongoing for us to see the scope of it. But then, yeah, it is a long-term project, and probably it will take at least a couple of years for us to have a concrete evidence of us enabling or us doing that. Yeah.
Yeah, that's quite significant. I mean, you said 100 times
Mm-hmm.
you reduce the water hungriness. I mean, that's water hunger
Yeah.
process. So
Yeah.
you reduce 100%. So qualitatively, if you ask, without much details, what are the major challenges to recycle this water? I mean, is there any?
There are challenges because we release chemicals and materials into the system, and also a lot of chemical reactions happen. So the wastewater is itself quite contaminated. So uh, there is a possibility of simpler recycling, filtration, and trying to send it to the RO treatment plant and things like that. Uh, it also depends on where the fab is located. So in the UK currently, water is not a significant challenge. So, but then if we want to deploy it to other parts of the world, then probably we need to consider recycling as much as possible. So the composition of the wastewater is the challenge here, and uh, even to send it out for the municipal wastewater treatment plant, you need to meet a certain requirements, or the characteristics of the wastewater should be within a certain limit. So we need to ensure that those can be achieved, and yeah, going forward, we would locally try to recycle as much as possible.
Thanks. And then let me check if we have any questions from the Q&A. No. So is there any comment on reducing the heavy metals or any toxic chemicals in the IC manufacturing? So you have any comment on that? Is there a way to reduce the toxic elements in the semiconductor manufacturing, or we use a process so that we can recover, or we safely recover those toxic chemicals, so we'll be eliminate the negative impact towards the
Yeah.
environment?
Okay. I mean, in the silicon nodes, I think that the most significant ones are the greenhouse gas uh, that is being emitted. So potentially these could be minimized by adopting an abatement system, which I think some of the fabs already implement worldwide. But I mean, in less regulated areas, they may not be doing the abatement, which is again an energy-intensive process. So the first step would be to abate as much as possible, and then try for alternative materials and chemicals in the process, which has a lower footprint and lesser toxic implications. So those would be the things to consider for the silicon nodes. For us, fortunately, we already use alternative materials, and our chemical usage is much less intense than the typical silicon node. So we are fortunate that we are able to work with this, and we are also deploying potential recycling options for our chemicals that would possibly enable us to reuse or recycle within the system so that it extracts the maximum value. But in some cases, it gets spent up. So in those cases, then probably we have to think of alternative options as
well. All right. That's a good comment. Thanks. Yeah. All right. So the last comment from my side is if you increase technology nodes, currently we are looking at sub 10 nanometer, sub 20 nanometer technology nodes. So if you're increasing your technology, FlexICs technology nodes towards in sub nanometer scale, so will it be feasible to maintain the sustainability aspect, or you see any challenges?
That's what we try to. We would strictly try and align to what we want from the sustainability aspect. So that's my role in the business as well. So I constantly overlook our technology development and see if any development that we make is aligning with our sustainability goals, and we want to ensure that the developments we make in the technology front doesn't compromise our sustainability aspect. So that's my role basically, and with every research project and every new options that we consider, we do an environmental assessment right at the start so that we don't find ourselves in a hotspot later. So yeah, we are trying to achieve sustainable development right from the scratch, and that is the best thing that is about my job currently.
All right, if there are no further questions, so I would like to thank Dr. Ashiq Ahamed again for this nice, insightful presentation, and I thank everyone for the participation. Thank you, Ashiq.
Thank you very much. Have a good day.